Okay, primes, so that we're now in 4.3. We've done modular arithmetic, more or less. And now we're on to primes and greatest common divisors. Okay, definition. This is a definition that we've seen like 3 times now. What is a prime? An integer p greater than 1 is prime if, man, I gotta do some better handwriting today. When is an integer prime? The only factors are 1 in itself. Yes. If its only factors just 1 second. My headphones are gonna die. I need to adjust. All right. Where was I? An integer is prime if its only factors are 1 and itself. Any other integer greater than 0, not prime, will be called composite. Okay, so here I have, so negative numbers, the correct way to think about negative numbers is that negative p should be considered as the same prime, is the same prime as p, technically. But if we only work with positive numbers, then we can forget about this distinction. So if you work with positive numbers, then 1 is not prime. 1 is called a unit. And then all of the other positive integers are divided into either being prime or being composite. But we won't need to worry about this. So usually when people are discussing primes in this context, we're just talking about positive integers. Is that okay? Hope so. So then now we have the fundamental theorem of arithmetic. Which fortuitously we have already proven. Every positive integer greater than 1 has a unique decomposition into a product of primes. Does anyone know how we would prove this? How we did prove this? The proof uses strong induction. Just for a quick sketch, I won't reprove the whole thing, but just to discuss, the idea is you start off by showing a base case, namely P of 2. So base case is 2, and 2 is a product of primes, namely 2 is equal to 2. This is a product of primes. Then the inductive case, or the inductive step, is you assume P of k is true for all n is equal to 2, well, 2 less than or equal to n all the way up to, let's say, r. And then you examine the number r plus 1. And this is either prime or composite. And if it's composite, then its factors, A, B, will land you back inside this set between 2 and R. Right? Are we okay remembering the idea for how this proof goes? Cool. I don't want to just redo the whole proof because we already did it. So that means that every integer, every positive integer can be written uniquely, and the uniqueness is important as a product of primes. So I don't know, let's pick a number. Let's pick some number lower than 100 so that I can do it pretty easily. What's an integer that we should find the prime factorization of? 27. 27, yes, I can do 27 very easily. 27 is equal to 3 cubed. Boom, done. 91, okay. 91, we have to think a little bit. 91, is 91 divisible by, okay. So what are the prime factors of 91? First of all, 91 is not divisible by 2. So I can make a little tree, 91. Is 91 divisible by 3? No, because 90 is divisible by 3. 91 is also not divisible by 5. So 2, no. 3, no. 5, no. 7. Is 91 divisible by 7? 70, 77, 84. It's divisible by 7. Great. So 91 is equal to 7 times 13. Is that true? Aha, beautiful. So 91 is equal to 7 times 13, and we have the prime factorization of 91, because indeed both of these are primes. So really I can think of this as 7 to the 1 times 13 to the 1. 99 will also have a nice prime factorization. This one I know. This is equal to 9 times 11. Well, 11 is prime, but 9 isn't. So this is equal to 3 squared times 11. And now I've written it as a product of primes. 3 is a prime and 11 is a prime. So I have a decomposition of my integers in terms of products of primes. I imagine that this is not new to y'all, but y'all have played these games before, right? Okay, I hope so. Here's a theorem to help us think about these. Theorem. Maybe I'll do a sketch first. So idea. When you are checking whether or not n is prime, you need only check primes that are less than or equal to square root of n. In other words, when I was examining 91, the square root of 91 is less than 10. So the point is, I only ever need to consider primes which are less than 10 when I'm trying to find whether or not 91 is a, when I'm trying to find the prime factorization of 91. So only need to consider 2, 3, 5, 7. These are the only primes that I need to look at in order to get a handle on the prime decomposition of 91. Can anyone tell me why? Anything above will be redundant. So what do you mean by that? Yeah, so the thing is, if I have a factorization of 91 into two different numbers, so let's say 91 is equal to a times b, well, I can't have it that both a and b are greater than square root of n, because then when I multiply them together, I get something that's bigger than n. Right, exactly. So it's quite possible that right, for instance, 91 did have a prime larger than the range that I described, but that's because it is a multiple of one that's inside the range that I was talking about. So I think that you guys kind of understand what I'm describing here, so I can write the theorem. If n is composite, n has a prime factor less than or equal to square root of n. And the proof is pretty much identical to what we were discussing. So let n be composite. So what can I do if n is composite? Yeah, I could do one of two things. I could either write it as a product of primes, so I could write n is equal to p1 to the a1 times pk to the nk. That's one thing that I could do. But also I could write also n is equal to a times b, where a and b are not 1. So I must have, let's see, 2 less than or equal to a less than or equal to b less than n, right? So it is correct that I can always do a prime decomposition, and this is like a smaller step than the full prime decomposition. I just say, well, if it's composite, I can write it as a product of two numbers. And moreover, those two numbers are not both either one or the number itself, right? If it's composite, it is not the case that its only factors are one in itself. So I must have some distinct factor a, which is greater than or equal to 2 and less than n. And then there's a b such that I can write n is equal to ab. I claim that either a or b is less than or equal to square root of n. If this were not the case, then a and b are both greater than square root of n. So a times b is greater than square root of n times square root of n, which is equal to n, a contradiction. So now I've at least produced a factor which is less than a square root of n. So without loss of generality, let a less than or equal to square root of n. Then take a prime decomposition of a. These primes are less than a. So less than square root of n. So p. If I want to write my prime decomposition of A as A is equal to P1 to the A1 all the way up to PL to the AL. So now, once you found an entire number which is less than or equal to the square root of n, then any of the primes in here are less than or equal to the square root of n. So I just take one of those primes. Right. I should put less than or equal to because it's possible that A is prime. Okay. Oh, I'm sorry. I'm so sorry. Any questions about this? Thank you. I think that this was pretty much exactly the idea that y'all had. I just wrote it out a little longer. Is this okay? Cool. Okay. So now, with these facts about primes kind of, oh, well, I guess we should do one or two more examples. Let's see. Let's show 137 is prime. And all that I need to do to show that 137 is prime is what? Right. So the square root of 137, or let's say 137 is less than the square root, less than 144. So the square root of 137 is less than 12. So I only need to consider primes 2, 3, 5, 7, and 11. If 137 is not divisible by any of these primes, then 137 must be prime itself. Do we agree? So 137 is not divisible by 2. That's clear from the last one. Divisible by 3. It's also not divisible by 3 because 137 is equal to 120 plus 17. This is divisible by 3, but 17 is not divisible by 3. So 3 is out. 5 is out because the last digit isn't a 0 or a 5. 7 is a little trickier, but 7 divides 140. And if 7 divides 140, 7 can't divide 137, right? Because that's 3 less. So 7 is out. And lastly, 11 is also out because 11 divides 121. So it's like 121, 132, 143. But 137 isn't one of these. So, okay, 137 is prime. Exactly, we just check all the primes below 12, and it ends up being a pretty easy task. Very messy and confusing when I write it out like this on paper, but hopefully y'all are okay with this. Yeah. Okay. I'm like really tired. Okay. Or sometimes I wonder if I, no. Let's do a very famous proof. This is a proof on the magnitude. Okay, so maybe I will let y'all give a minute and tell me what you think some of the coolest proofs in this class have been. The square root 2 proof is an excellent proof, and it's also an ancient proof. Yep. So among the coolest proofs in the class is square root 2 is irrational. That's definitely one. The murder adds a lot, I agree. The murder by throwing someone off of a boat. Okay, so this is like antiquity. Some other extremely cool proofs are countability of Q and uncountability of R, and the cardinality of a set is always less than the cardinality of the power set. These are also extremely cool proofs. The root 2 to the power of root 2, yeah, to show that there is a that there must exist a pair of irrational numbers a and b such that a to the b is rational. That's also a very cool proof. Okay, so this next proof belongs in this category of extremely cool proofs, and this is the infinitude of primes. Okay, and this one is known for thousands of years. Okay, theorem. There are infinitely many primes. Okay, and we're going to prove this by contradiction. Assume, for the sake of contradiction, that there are finitely many primes. And if there are finitely many primes, I can list them out, right? If there are finitely many, I can just say there's P1, which is going to be 2. There's P2, which is going to be 3. P3, which is going to be 5. All the way up to PK. And then who knows what the last prime is, but there's some finite list of primes, and I can list them all off like this, right? So I'm assuming there are finitely many primes and that I've got them all. So now we produce a new number. Now we consider Q, which is going to be equal to the product of all these primes, P1 times P2 times P3 times PK plus 1. Okay? Are we comfortable with what I've done so far? I have assumed there are finitely many primes. I've multiplied all my primes together and I've added 1. Okay, there are two options for Q, right? So Q is either what or what? Indeed, why did I add 1? We shall see. Q is either prime or composite. Case 1. If Q is prime, we have produced a new prime. Not on our list. Right? Because Q is certainly bigger than any of the P1 through PK, because it's the product of a bunch of all these positive numbers, and then I've added 1. In fact, I don't even need to add the 1 here. If I take the product of a bunch of positive numbers, that product is bigger than any of the individual numbers, right? So if Q is prime, then Q is a prime which is not on my list of finitely many primes. Do we agree? This contradicts our assumption that we have listed all the primes, that our list P1 through Pk is a complete list. Okay, case 2 is that Q is composite. So Q has a prime factorization. Right? So now my question is, if Q has a prime factorization, is Q divisible by my set of primes? So I'll write Q is equal to P1 to the Q1 times Pk to the Qk. And in particular, Q is divisible by at least one prime, P on my list. Exactly. However, for Pi on my list, Pi cannot divide Q, because if Pi divides Q and Pi divides P1 all the way up through Pk, then Pi divides 1. This is a contradiction. So this 1 is around to say that if any of these primes divided Q, then it would have to, since it divides this term and it divides this term, it must divide this term, but no prime divides 1. Right? If P, so let's say A is equal to B plus C, if P divides A and P divides B, then P divides C, because C is equal to A minus B, and P divides both parts of this. So we have shown that all the primes on the list cannot divide Q. This is a contradiction. Box. Okay. Any questions here? I agree. This is a super cool proof. There are a couple things to notice. One, we did not, so this proof is non-constructive. In the sense that Pi cannot divide Q, because if Pi divided Q, and since I know that Pi divides the product of primes, then Pi must divide 1, and this is a contradiction. Yeah, so here it's Pi cannot divide Q. that help? So PI was PK plus 1? No. So the point here is that if Q is composite, Q must be divisible by some prime. But it's not divisible by any of the primes on this list, because if it were, right, like let's consider P1. Let's say, is Q divisible by P1? Let me go over here. No, because 2 is a prime, right? So this product of primes is definitely going to be even. Right? Oh, right, this Q is going to be odd. So let me say, so Q is equal to P1 all the way up to PK plus 1. So question, is Q divisible, not Q, is Q divisible by P1? And the answer is no, because if P1 divides Q, then since P1 also divides P1 times PK, then P1 must divide Q minus P1 times PK, which means P1 divides 1, a contradiction. So Q is not divisible by P1. And this exact argument works for all of the primes on this list, all of the primes that appear in this product. So PI was just an arbitrary prime on the list. And Alex, are you okay with what your statement is not quite correct?
Yeah, I meant like if we said that it was a product of any number greater than 2 primes. So like if it was 2 times okay, I see now. Okay. Even okay.
Right.
Yeah, I'm good.
So there are a couple of things, but one thing is that if 2 is on our list and we know 2 is prime, then this product will always be even. So an even number plus an odd number will always be odd. So the number that I've constructed here, Q, you can think of it as being an odd number. And we really don't know, I mean, okay. What this proof shows is that if there are finitely many primes and we multiply them all up and add 1 in this way, then Q cannot, well, it's either prime and then we have a contradiction, or it's composite and we also have a contradiction. Both of them contradicting the fact that we have a finite list of primes and that we have all of them on our list. There's some kind of, I mean, there's some interesting math going on here. So please, if you have a question, please ask. So an important thing, right, is one, this is a non-constructive proof. In the sense that this proof did not present to us a new prime. We did not state that Q is prime. It's either prime or composite. It's not the case that I know that Q is prime, right? So I haven't constructed a new prime by this process. In other words, this proof doesn't tell you how to find additional primes. It just tells you that there can't be finitely many. Any further questions here? Okay. Extremely cool proof. To my knowledge, no one got killed for this one, but still very cool. The second step of case 2. Okay, so case 2 is Q is composite, and so it must have a prime factorization, right? So Q having a prime factorization means that one of the primes in the universe must divide Q, right? But I'm also assuming that all of the primes in the universe are on this list, this finite list from P1 to Pk. And I've specifically built a number Q whose whole reason of existence is that it is not divisible by any of these numbers on the list.
Okay, I think that might be the part I'm confused about.
So why is Q not divisible by any prime on this list?
Yes.
Okay. Um, let's let's do some examples. So let's build a number 2 times 3 times 5 plus 1. So this is some collection of primes plus 1. This is actually equal to 31. My question is 31 divisible by 2, 3, or 5? Well, on one hand, you can just look at it and say, 31 is not divisible by 2, 3, or 5, but maybe a better reason for why 31 is not divisible by 2, 3, or 5 is that 31 is equal to 2 times 3 times 5 minus 1. So if 2 divided 31, then 2 would divide 2 times 3 times 5 minus 1. This whole thing. Okay, I know 2 divides 2 times 3 times 5, right?
Yeah.
If 2 divides this piece and 2 divides the whole thing, does that tell me anything about 2 dividing this last chunk?
Yeah, that it can't.
Well, if 2 divides, so if 2 divides A and 2 divides A plus B, then 2 must divide B. Are you okay with this?
Yes. So is it that we would be saying that 2 divides 1?
Exactly, exactly. If so 2 always divides this product because 2 is in this product. So if we assume that 2 divides this whole thing, then 2 must divide 1, which is a contradiction. Or which
Okay.
is false because 2 does not divide 1.
Okay, that makes sense. But like, what if we're not dealing with 2?
Well, let's try it with 3. Can 3 divide 2 times 3 times 5 plus 1? Well, sorry, this should be a plus 1, right? Can 3 divide this thing? 3 divides 2 times 3 times 5. So this is the same thing. If 3 divides A and 3 divides A plus B, do I know that 3 has to divide B?
Oh, yes.
Then
Okay.
3 must divide B. But in this case, B is 1, and it's false that 3 divides 1. So
Okay.
3 cannot divide this whole thing.
Okay, thank you. This makes sense now.
And it's the same with 5. Every prime on this list cannot divide the product plus 1, because if they divided the whole thing, that would mean they divided 1.
Okay, thank you.
Yeah, sure. So that's the idea. That's why we cooked up this number q. This q is a number that is built specifically so that it is not divisible by any p1, p2, p3, all the way up to pk. It is not divisible by any of these numbers.
Okay.
Because if it were, then that number, that prime, would divide 1. Yeah. Yeah, thank you for your question. It's something to kind of work through. Yeah. Good question. Any further questions on this proof or on divisibility? Should I prove actually that if P divides A and P divides A plus B, then P divides B? I can just prove this. Yeah, okay. So these two things say, so by definition, P divides A means A is equal to what? P times K, yep. Similarly, A plus B must be equal to P times K2. So if I substitute P times K for A, I see P times K plus B is equal to P times K2, or B is equal to P times K2 minus P times K, which is equal to P times K2 minus K. So P divides B because B is equal to some integer times P. And here I didn't use prime. I didn't use that P was prime at all. This is for division. If any integer divides A and divides its sum, then it divides the other summand. Is this okay? Probably if I had had some foresight, I would have proven this explicitly before embarking on this proof, huh? Well, you live and you learn. Actually, probably you live and you don't learn, because I think that I made the same mistake last year when I taught this. Anyways, third time's a charm. Exactly. You know, the infinitude of primes is a good high note to leave class on. So I think we're good for today. You're free to ask me more questions, but you know, it's a Friday. We've got 3 weeks left. Y'all can head out 5 minutes early. That's a reasonable thing. I will be assigning some problems for homework. That'll be due Monday, but most of the problems you've had for a while, so I won't be adding too many problems on primes. What is the exact date of the exam? Well, it's not next week. And so next week I will tell you what the exact date of the exam is, but it should be the week after. Sorry that I can't be more explicit. Sure. Oh yeah, I still have not posted midterm 2. I'm gonna do that actually very soon this morning. Sorry, I'm gonna send that in an email to everyone. Sorry about that. Okay. Yeah. Have a great weekend, everyone.
Thank you.
Yeah. Thank you too.